In this lesson, we're going to be talking about the binomial distribution. There are 4 conditions to the binomial setting. The first one, we have to have 2 outcomes that can be labeled as success or failure. So, for instance, flipping a coin. That's an easy one because we only have 2 outcomes, heads versus tails. So we could label heads as success and tails as a failure, or vice versa. But lots of things that have more than 2 outcomes could also fall under the binomial setting. So for instance, if we're rolling a die, right, we know there's 6 outcomes on the die. But if we label one of those outcomes a success, let's say the number 1 is our success, we could label 2 through 6 as failures, and now it becomes a binomial situation that only has 2 outcomes, the success of 1 and then the failure of 2 through 6. Okay, we also have to have a fixed number of trials, so we have to know how many times are we flipping the coin, or how many times are we rolling the die, or how many people are we selecting. This is an important one. We have to have independent events, so the probability of the first event cannot be affected by the next event. Okay, and then the probability of success has to stay consistent. That kind of goes hand in hand with independent events. All right, so let's take a look at the formula. I know it looks kind of complicated, but we're going to break it down. So I'll show you how it works in just a minute. So this in parentheses n over x is just shorthand for this part of the formula. Okay, so n factorial over n minus x factorial times x factorial. That is that in parentheses n over x. We multiply that by the probability of success, p, raised to the x power. That's how many successes we want. And then we multiply that by q, which is the probability of failure, raised to the n minus x power, or in other words, how many failures do we want? Okay, down here we did some variable identification, and I kind of said these as I was reading off the formula, but just in case, n is the number of trials. So how many times are we flipping the coin? Or how many times are we rolling the die? Or how many people are we selecting altogether? X is the number of successes that you want. So again, the success you define. P is the probability of success in just one trial. And then Q is the probability of failure in just one trial. Okay, so we're going to go ahead and take a look at some examples of those. All right, the first example says, a coin is flipped 5 times. What is the probability of getting 3 tails? Okay, so let's just go through and make sure that this is a binomial setting first. We're flipping a coin. So we have to make sure that that coin only has 2 outcomes, and we can label them as success versus failure. Because the probability that's being asked is of getting 3 tails, I'm going to say that tails is my success, and that means heads is the failure. So yes, it does have 2 outcomes that we can label as success and failure. We have to have a fixed number of trials. That's going to be represented by the letter N. We do know how many times we're flipping the coin. It's 5 times. So we do have a fixed number of trials. We have to have independent events. So if we think about flipping a coin, just because we got a tail on the first flip does not influence our next flip. So they are independent. And then the last one, our probability of success for one trial has to stay the same from flip to flip, which again, since it's independent, the probability is not going to change. So let's think about that probability of getting tails. Probability of success would be 1/2. Probability of failure, probability of heads, would also be 1/2. Okay, the only other value that I need to identify is x. N is the number of trials, where x is the number of successes. So I've identified the success as tails. So we need to figure out how many tails do we want out of those 5 flips. And here we want 3 tails. So x equals 3. Here's what the formula looks like. We're going to take n factorial divided by n minus x factorial times x factorial. If you're unsure about what those exclamation points, the factorial symbol, means, we're going to do it here in just a second. We're going to multiply that times p raised to the x power, and then multiply that times q raised to the n minus x power. Okay, let's go ahead and plug in those values. N we identified as 5. So 5 factorial divided by n minus x factorial. Well, n we said was 5 minus x, which is 3 factorial. And then in that denominator, multiplied by another x factorial. We're going to multiply that by the probability of success, which is 1/2. And we need to figure out how many of those successes do we want. We wanted 3 tails. Probability of failure, which is the probability of heads, we said was q, 1/2. And then we have to figure out how many of those do we want. So that's the n minus x power. So for this would be 5 minus 3. But if we think about it, guys, if we're flipping 3 tails and we flipped 5 times, we have to get 2 heads, right? So it's the number of failures, whatever that failure is identified as. Okay, this 5 factorial means that we're going to multiply 5 times 4 times 3 times 2 times 1. So a factorial will start at the number that's given, and you multiply by the numbers that are 1 less than the previous until you get all the way down to 1. Okay, so 5 minus 3 factorial, that's 2 factorial. So that would be 2 times 1. And then 3 factorial, that is 3 times 2 times 1. Again, we start at the number, and then we multiply by 1 less than the previous number until we get down to 1. Okay, and then we multiply that times 1/2 raised to the 3rd times 1/2 raised to the 2nd. Okay, now some of these numbers will reduce. So 3 times 2 times 1 will cancel with that 3 times 2 times 1. So I have here 20, 5 times 4 is 20, divided by 2. Well, that's 10. So guys, what that tells me is that if I were to write out flipping a coin 5 times and wanting 3 tails, that's one arrangement. But there's actually 10 arrangements of those letters. So if I move those H's to different slots, let's say, for instance, I want heads, heads, tails, 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 or heads, tails, heads, tails, tails, right? All those different arrangements, there's 10 of them. So that's what this part of the formula tells you how many different ways you can rearrange those letters. Okay, so we have 10 multiplied by 1/2 to the 3rd. Well, that would be an 1/8 times 1/2 squared. That would be a 4th. Okay, I'm going to take out my calculator and go ahead and multiply those. 10 times 1/8 times 1/4. I get 0.3125 as a decimal. I could, again, write that in any form. So if I wanted to change that to a fraction, that's 5/16. Or I could write it as a percentage, 31.25%. Okay, so again, any form for probability that you'd like. Okay, let's take a look at the next example. This example says, a 6-sided number cube is rolled 10 times. What is the probability of getting 3 6s? Okay, so again, let's double check that this is a binomial setting. First of all, rolling a number cube. We know that it has 6 outcomes. So we better be able to group outcomes into success and failure. So if we look at the question, what is the probability of getting 3 6s? 6 is going to be the success. So that means the failure are the numbers 1 through 5. So we grouped them into 2 outcomes. So we're good to go there. The next one, we have to have a fixed number of trials. So we know that we're rolling the number cube 10 times. So n is 10. So we do have a fixed number of trials. Rolling a number cube needs to be independent events. So if we roll a 6, we have to think, are we more or less likely of rolling a 6? No, it's independent, so that's good. And then the last one, the probability of success, has to stay the same per trial. So again, our success was rolling a 6. So that probability is 1/6 for each trial, and it's not going to change. Okay, let's identify Q, which is the probability of failure. Now remember, we grouped these together. So there's 5 outcomes there. 1, 2, 3, 4, 5. So the probability is 5/6. So the probability of success, P, plus the probability of failure, Q, had better always equal 1. They are complements of one another. So little side note there. Okay, the last thing we need to identify is N, which is the number of successes. So how many 6s do we want out of those 10 rolls? And right here it says we want 3. Oh, and I just labeled that as N again. Sorry, you guys, that needs to be X. X is the number of successes. Okay, here's the formula. We take N factorial over N minus X factorial times X factorial times P to the X times Q to the N minus X. Okay, if we plug in those numbers, N is 10 over 10 minus 3 factorial times 3 factorial times the probability of success, which is 1/6, and we want 3 of them, times the probability of failure, which is 5/6. And if we're rolling the die 10 times and we want 3 6s, that would leave 7 non-6s. Okay, you could also just take 10 minus 3 to get that exponent. Okay, if we go ahead and show the work here, 10 factorial, we're going to be multiplying those numbers all the way down to 1. Ten minus 3 factorial, that's 7 factorial. So then we're going to multiply 7 all the way down to 1. Times another 3 factorial. So that's 3 times 2 times 1. Okay, 1/6 to the 3rd, and then times 5/6 to the 7th. Okay, again, a lot of these numbers will cancel out. That's 7 down to 1. I could cancel. 3 times 2 times 1 is 6. And 10 times 9 times 8. 90 times 8, 720. Okay, so there's a lot more of arrangements here than the last time. What is 720 divided by 6? We have 120 different arrangements. Whew, I would not want to do that by hand. We're going to multiply that 120 by the probability of 1/6 to the 3rd times 5/6 to the 7th. I'm going to go ahead and do that. And I get 0.155 as my final answer. Ooh, sorry, I'm out of room there. 0.155. Again, I could hit math enter if I wanted it as a fraction. Oh, and the calculator is not converting that to a fraction, I guess because it's so small. So we'll keep it as a decimal. Or you could change it to a percentage, 15.5% if we wanted to change it to a percentage. Okay, let's take a look at our next one. This one says, the probability of an archer hitting a target is 62%. If this archer aims at the target 15 times, what is the probability that he or she will hit the target exactly 12 times? Okay, let's go ahead and identify this as a binomial setting and identify n, x, p, and q. Okay, so n is the fixed number of trials. And we see that that's 15 times. X is the number of successes. We want that person to hit the target 12 times. So hit is my success. The probability of hitting the target was given as 0.62, and I'd have to make sure that those are independent. So just because I hit the target the first time does not make me any more or less likely to hit the target the next time. So target shooting is independent. And then Q, so if the probability of hitting the target is 0.62, the probability of not hitting the target would be 0.38. Again, we make sure that if we add P plus Q, those always have to equal 1, which it does. Okay, so we kind of went through the checks as I was identifying those, but we determined that they are independent. You either hit the target or you don't, so there's 2 outcomes that we could label as success and failure. We have a fixed number of trials, that's 15, and they are independent. The probability of success does not change from hit to hit. Okay, I think I got them all there. So if we plug in these values, we have 15 factorial divided by n minus x factorial. So 15 minus 12 factorial, and then divided by x factorial, times the probability of success, which is p, raised to the x power. We want 12 of those hits, and 38% is the probability that we will miss the target. And if we shot 15 times and hit 12 times, we'd only miss 3 times. Okay, let's go ahead and calculate that out. So 15 factorial. I'm not going to write out all those numbers. We're going to have 15 times 14 times all the way down to 1 over 15 minus 12, that would be 3 factorial. So 3 times 2 times 1. And then 12 factorial. So 12 all the way down to 1. Oops, I don't need that exclamation point anymore. Let me erase that out of there. Okay. Then we'd have 0.62 raised to the 12th and times 0.38 raised to the 3rd. Okay, I'm going to show you a little shortcut here, guys, because these can get kind of lengthy. Okay, there is a function in your calculator called NCR. That is the same as NCX. Okay, so if we identify N, which in this case is 15, the C stands for it's a combination. How many different arrangements do we want? And then the X is 12. This function can be found under math over to PRB, and it's number 3. You do have to enter the 15 in your calculator first, then hit the math key over to PRB for probability, and then down to option number 3, NCR, and then hit the 12. So we get 455 arrangements. So when I simplify this part, I get 455. Okay, the calculator again can make that quicker. We're going to multiply that times 0.62 to the 12th and times 0.38 to the third. Let's go ahead and do that. Okay, I got 0.0805 as my final answer. Okay, this next question, what is the probability that he or she will hit the target at least 12 times? So if we want at least 12, that means 12, which we already found, or 13, or 14, or all 15, right? We were flipping, or we were target shooting 15 times. So this is actually 1, 2, 3, 4 probabilities that we have to find separately. And hopefully we're thinking what or means. Or means addition. So once I find these probabilities, I would need to add them up. Take a minute, see if you can find, we know the probability of 12, we just did it a second ago, 0.0805. See if you can find the probability of 13, the probability of 14, the probability of 15. Fill those in, add them all up, and we'll see what we get. So pause the video here, find those probabilities, and then unpause it to see the results. Okay, I found those other 3 probabilities as 0.0303 for 13 hits, for 14 hits, 0.0071, and for 15 hits, 0.0008. Now, this last one was given in scientific notation in the calculator. So when I saw that number, it said 7 point something e to the negative 4. Okay, this number here was bigger than 5. I don't remember what it was exactly, so I rounded this to 8. But that e to the negative 4 means I have to move that decimal 4 spots to the left. So that fills in 3 zeros in those missing slots. So that's how I got that 0.0008. So watch for those scientific notation answers in your calculator. It'll look like e to the negative number. Just that number tells you how many places you have to move to the left, the decimal place to the left. Okay. Last example, before we talk about finding mean, standard deviation, and variance for these binomial situations. So it says a manufacturer of metal pistons finds that on average 12% of his pistons are rejected because they are either oversized or undersized. What is the probability that a batch of 10 pistons will contain no more than 2 rejects? Okay, so in this particular scenario, you have the choice of identifying your success or failure. I would probably identify the reject as my success. It's kind of crazy, but that's what I would do. My success is the reject part. Okay, so my failure would actually be if it's a good part. Now, you can switch those around if you want, but again, it's just going to change your numbers. But we are selecting 10 pistons, so that's N. Probability of success, which is getting a reject, was given as 12%. So that means the probability of failure, or the probability of selecting a good part, would be 88%. And X is the number of successes. We want no more than 2 rejects. So that means we would want 0 rejects, or 1 reject, or 2 rejects. So guys, this is another one that we're going to have 3 probabilities. So for the X equals 0, for the X equals 1, and for the X equals 2. And again, those would be separated by or. We want 0 rejects, or 1 reject, or 2 rejects. So we're going to find those 3 probabilities and add them together. Again, pause the video here and we'll talk about answer in a minute. Okay, check those probabilities. I got 0.2785, 0.3798, and 0.2330. I added those up and got a final answer of 89.13%. Now, I forgot to mention on that last example, we are rounding. I'm rounding to the 4th decimal place here. So there might be just a little bit of rounding error there because we are rounding each one of these probabilities to the 4th decimal place. So that's causing a little bit of rounding error with our answer as well. That's fine. Okay, let's go ahead and take a look at how do we calculate the mean, variance, and standard deviation for binomials. The mean is that we're going to multiply n times p, so the number of trials times the probability of success. For variance, we're multiplying n times p times q. So number of trials times probability of success times probability of failure. And hopefully we already know that we just take the square root of the variance to get the standard deviation. Okay, our first example that we're going to take a look at for calculating those is that archer example that we looked at before. So the probability of hitting a target is 62%. The archer is aiming 15 times, and we want to know what is the mean number of times he or she will hit the target. So to find the mean, we multiply n times p. So n here is 15 times, and our probability of hitting is 0.62. So let's go ahead and multiply those, and that's going to tell me on average how many times is he or she going to hit the target. I get 9.3. Now, even though we either hit the target 9 times or we hit the target 10 times, our average does not have to be a number in the data set. So on average, she would hit the target 9.3 times. I want to keep that, right? Our rounding rules, we keep at least 1 decimal place. Okay, it's just like the census says on average, the number of children per family is 2.4. Obviously, you can't have 0.4 of a child, okay? But on average, we're adding everybody's together and dividing by the number in our population. So here, we're taking all of those hits and dividing by the number of times he or she aimed. Okay, so again, it does not have to be a number in the data set. So do not round that to a whole number. It's an average. Okay, the second question, what is the variance for the number of hits? So we're going to multiply n times p times q. So 15 times 0.62 times 0.38 is the probability of miss. Okay, let's go ahead and multiply that. And we get a variance of 3.53. I'm just going to round that to 3.5. Okay, and then we take the standard deviation is the square root of the variance. Okay, so the square root of 15 times 0.62 times 0.38. For our example, we're taking the square root of that 3.5 that we just got from the last answer. And I get 1.88 if I round to 2 decimal places. I guess if I was rounding to 1, I could say that that was 1.9. Again, I accept a range of values as long as you're not rounding to a whole number. Keep at least 1 decimal place and appropriate rounding to that decimal place. Okay, our last example for this lesson is another example with mean and standard deviation. I did not ask variance on this one, so I could, but I just didn't. A manufacturer of metal pistons finds that on average, 12% of his pistons are rejected because they're either oversized or undersized. In that batch of 10 pistons, what is the mean number of rejects? Again, rejects is our success. So we're going to multiply n, the number that is in the sample or the trial, which is 10, times the probability of being a reject, which is 0.12. If we multiply that, we get on average 1.2 rejects. Again, it's an average, so I'm not going to round that to a whole number, even though you can only have either one reject or two rejects, right? We're not going to round that because, again, it's a mean. The standard deviation, we're going to take the square root of n times p times q. If 12% are rejects, that means 88% of pistons are good. Okay, let's go ahead and multiply that. And make sure that we are taking the square root of that number. And I get 1.03. I'm rounding that to 2 decimal places. Okay, so out of a batch of 10, on average, we're going to have 1.2 rejects. And those numbers vary from the mean on average by 1.03 rejects. Okay, this concludes the lesson for today.